Assalamu alaikum, dear student. This is lecture number 3 of week number 8, and this is the final lecture on dimension analysis. So let's see the learning objective that we have achieved so far. So now we are doing some practical problems, okay, to understand the concept of modeling and similitude to develop prediction equations. Okay, so far we have covered the learning objective up to this point, and let's move on the topic we are going to cover today. So today we are just solving some practice problems. So let's start. So here the problem is a glycerine at 20 degrees centigrade flows with a velocity of 4 meter per second through a 30 mm diameter tube. Okay, so here we are not talking about the material of the tube, we are just talking about the flow. So here we are talking about the flow and the diameter. A model of this system is to be developed using standard air as the model fluid. Okay, the air velocity is to be 2 meter per second. Okay, so what tube diameter is required for the model if dynamic similarity is to be maintained between model and prototype? Okay, so here you can see what are the informations are given. First of all, we note down, we should make a data for that. So the temperature of the glycerine is given, the velocity of the fluid flow is given, and the diameter of the prototype is given. So these are the information about the prototype. Okay, so now to test now to find out the flow, okay, a model we have to develop. Okay, so a model of this system is to be developed using standard air. So instead of that, we do not have the glycerine available, so we are going to test the same phenomena with the air. Okay, so the air velocity is to be 2 meter per second. Okay, the air velocity is given. So what tube diameter is required for the model if dynamic similarity to be maintained? So we have to find out the model diameter to use water as a working fluid. So you know, whenever we talk about the pipe flow or the open channel flow, okay, so whenever we talk about the fluid flow, so always there is a dimensionless number which comes in our mind, that is a Reynolds number. Okay, because basically the Reynolds number is the relationship between the flow properties of the fluid flow. Okay, so here we will consider, because all the data are given, diameter is given, velocity is given. Okay, and so we have to the Reynolds number basic, and also the glycerine, the density is given, and the viscosity of glycerine, obviously we can get it. Okay, so all the material properties are given. So basically the Reynolds number relates the velocity with the material properties and the dimensions of the pipe or channel, whatever you have. So in that case, we are going to use a dimensionless parameter to satisfy the dynamic similarity. And also I have explained in my lecture previously that for the dynamic similarity we consider one of the dimensionless parameter, okay, which relates all the variables. Okay, so here we are going to consider for dynamic similarity the Reynolds number must be same for model and prototype. Okay, so this is the Reynolds number for the model, and this is the Reynolds number for the prototype, and this is the Reynolds number in the form of kinematic viscosity. Okay, so we can write also this in the form of dynamic viscosity also, but in the dynamic viscosity you know that we have 4 variables. Okay, so we replace the density and the dynamic viscosity with one term with a kinematic viscosity. Okay, so if you go to the table, you can find out the kinematic viscosity for the glycerine at 20 degrees centigrade, and also you can find out the viscosity of the air. Okay, so now we are going to relate what we have to find out. We have to find out the diameter of the model. Okay, so what tube diameter is required for the model? So we have to separate dm. So we separated dm with all the variables. Okay, so here this is the viscosity ratio and here is the velocity ratio. So the velocities are given and the viscosities we can find out from the table. Okay, and we inserted the values and multiplied by the diameter of the prototype is given d. Okay, that is 0.030. Okay, so finally we can calculate diameter of the tube. So that is going to be 0.736 mm. You can see that it's very small. Okay, so if we use this kind of because air is the fluid. Okay, so almost less than 1 mm. Okay, so this is the solution of this problem. So let's move on to the another practice problem. So here a solid block in the shape of a cube rests partially submerged on a bottom of a river as shown in the figure. So here is the figure. This is the block, okay, and this is the water, or this is the river, okay, and we put this block in the path of the river, okay, and partially submerged. It is not completely submerged, it is partially submerged in water, in the river water, okay, and it is rest at the bottom. So the drag D on the block depends on the river depth. So the drag force exerted by the river on the block is depending on D, the block dimension, H, the stream. The drag D on the block depends on the river depth. So the river depth is D. Okay. The block dimension H, so this is the block height H, okay, block width H, and possibly if it is a square, so it is cube, okay, shape of a cube. So if it is a cube, so this is H H H, okay, so height of this cube is also H, okay, depends on the river depth and the block dimension H, the stream velocity V, and the fluid density rho, and the acceleration of gravity g. Okay, because the fluid has some height, so definitely it has some weight on it. Okay, so what we have to do, we have to perform a dimensional analysis for this problem. So first of all, we have to perform a dimension analysis. The first step, we have to determine the number of pi terms for this practical problem. Okay. Okay, number 2, the drag is to be determined from a model study and using a length scale of 1:5. So length ratio is given. Okay, so the whatever is the length of the prototype and whatever is the length of the model, so the ratio between the length of the prototype and the model is 1:5. Okay, so what model velocity should be used to predict the drag on the prototype located in a river with a velocity of 9 feet per second? Okay, so we have to determine the drag force on the prototype, okay, located in the, so we have to determine the drag force on this block, okay, on the prototype. Okay, and the river velocity is 9 feet per second. And the river velocity is given 9 in the real condition. The river is flowing with a velocity of 9 feet per second, and the length ratio between the real size block, the size of the prototype, and the size of the model is 1:5. Okay, so water is to be used for the model fluid. So for the model fluid, water we are going to use as a fluid. So determine the expected prototype drag in terms of model drag. So we have to find out the drag force in term we have to find out the drag force of prototype in terms of drag force on the model. Okay, so first step is to find out the total number of dependent and independent variables. So let's see here. So this is the total number of variables we have. So and we have converted them into fundamental dimensions. And from the pi term, okay, the total number of dependent variables is 3 and the total number of reference dimensions are 3, so is equal to 3 pi terms required, and the dimension analysis yields. Okay, so here first of all, after solving all the by using the pi theorem, so this is the combination of the variables, okay, that is finally got in the form of dimensionless number. So these are the pi terms for the prototype. Okay, so now we are going to now to solve the problem part B, we are going to write down the pi terms for the models. So this is pi 1, pi 2 and pi 3. So pi 1 and pi 2, so this term in the form of model dm over hm, so this is for the model and this is for the prototype, and same here, this is for the model and this is for the prototype, and same we can write for this as well. Okay, so here since the ratio is given, okay, so what is the ratio? So the diameter of the model over the diameter of the so we separate with each other. Okay, so we took the diameter underneath and h is going up, so the ratio between the diameter of the model and the diameter of the the depth of the river fluid of the model and depth of the river fluid D, okay, and height of the model block and height of the prototype is ratio is given, that is 1:5. Okay, if the model size is 1, then the prototype size would be 5 times greater than the model. Okay, so this ratio was given. Okay, the geometrical ratio is given. So whatever is the shape or whatever is the linear shape of the geometry, whether it is curve or whether it is a straight line, okay, it will be reduced, okay, with a factor of 1:5. Okay, so this geometrical ratio was given. So now we can write down for the okay, so for the velocity of the model we can write down the next relationship we used it. So gm over g, the model, the gravitational acceleration for the model and for the prototype, and this equation we use it from here. Okay, this is the equation we have, this is the pi 3. Okay, so we equate them and finally we separate them, because we have to find out what we have to find out. We have to find out what model velocity. We have to find out the model velocity to be used to drag on the prototype located in a river with the velocity of this. So we have to find out the model velocity. So let's use so here, so this is the model velocity, we separate them together. So this is the dimensional ratio and this is the acceleration ratio. So we know this value and we know this value, we separate them. So normally we write the terms in the form of ratios, yani the dimension of model and dimension of prototype. So we write down in the form of ratios. So all the values are given. So finally the velocity of model is 4.02 feet per second instead of 9 feet per second. Okay, so third term we have to find out the relation between we have to predict the equation for the drag force on the prototype in terms of the drag force of model. Okay, so here the third term we have used, you can see this is our third term. So this is written for the this is for the prototype. Now we are going to write down for the model. So this is for the prototype and this for the model. So this is the drag force that we have to determine in the form of dm. So we took this all value there. So rho over rho m, okay, density of the fluid in the river and density of the fluid used in the model, velocity of the river fluid, and the velocity of the fluid using in the model. So height of the block, the actual height of the block or the prototype, and height of the model used in the laboratory. And this is the drag force, okay, on this is the drag force on the model block. Okay, so we know the densities, we know this all. So we inserted all those values, okay, h over hm. Okay, so basically hm over h was 1 over 5, so here h over hm, so definitely is going to be reverse. Okay, so that will be equal to 5, yani 5 over 1. So this ratio will be 5 over 1. This we know that 9, this we have calculated 4.02. And since in both the cases we are using water, so because in that case the density of the water will be same and they're going to be cancel each other. So we will have the relationship is 125 times the drag of the model. So this is the solution of this problem. So let's move on to another problem, that is the pressure rise delta P across a centrifugal pump of a given shape can be expressed as delta P is a function of diameter, okay, diameter of the impeller, and the angular velocity, density of fluid, and the flow through the pump. Okay, so here where d is the impeller diameter, so delta pressure drop is the function of these four variables. So where d is the impeller diameter, omega is the angular velocity of the impeller, rho the fluid density, and q the volume, rate of flow through the pump. A model pump, okay, a model pump having a diameter of 8 inches, okay, is tested in the laboratory using water. Okay, when operated at an angular velocity of 40 pi radian per second, the model pressure rise as a function of q is shown in the figure. Okay, when we tested the model with the impeller diameter of 8 inches and the velocity of the impeller was this, okay, based on that the relation we found between the pressure drop and the flow showing in the graph. Okay, so this is the relationship between the model pressure drop across the model pump and the flow in through the pressure pump. So here you can see as the pressure drop is decreasing, the flow is increasing. We all know that because you see, if you all have experience at home, the pump you have, when you throw the pump, sorry, when you start the pump and you have a pipe hose in your hand, so you see the volume flow rate is much higher. So same water if you throw to your overhead tank, okay, it takes more time to fill the tank. So if you throw the water more higher level, the flow rate will start decreasing because the pressure head is increasing. So as the pressure head is increasing, okay, the flow rate is decreasing. You can see that. So this is the flow rate is 0.5 feet cube per second. So if you are going further higher, so it's going to be 0 at this point. Okay, so this is the maximum point where maximum height it can flow the water with 0.1 feet cube per second. So as the pressure drop is reducing, as the height is reducing, the flow rate is increasing. Okay, so here the graph is given. Okay, so when use this curve to predict, so we have to use this curve to predict the pressure rise across a geometrically similar pump. Okay, prototype for it's given that pumps are geometrically similar. Okay, for a prototype flow rate, for the prototype flow rate 6 feet cube per second. If the prototype flow rate is 6 feet cube per second, okay, So the prototype has a diameter of 12 inches and operates at an angular velocity of 60 pi radians per second. So the prototype fluid is also water. So here basically what exactly we have to do, we have to predict the pressure rise across a geometrically similar pump for a prototype flow rate. So we have to make a relationship between the pressure drop of the prototype and the pressure drop of the model. Okay, so first of all what we have to do, we have to determine the pi terms. Okay, so here the total number of variables are given. So we converted all of them into its basic all the variables into its basic dimensions. So the total number of pi terms we needed to this is 2 pi terms. So we, after solving that, we got these 2 pi terms. Okay, so these 2 pi terms for the prototype. Okay, so this is the delta P of the prototype, and this is the volume flow rate. This is the pi term included with volume flow rate of the prototype. So now we are going to write down the same pi terms for the models. Okay, so thus the similarity requirement is, we write down, this is for the first term for the flow. Okay, this is the similarity requirement is the volume flow rate. Okay, so this is the pi 2 terms, this is pi 2. So this is the pi 2 of the model and pi 2 of the prototype. Okay, so now because the volume flow rate of the model is given, okay, so we can determine the volume flow rate of the prototype by using this. Okay, and diameters are given and the angular velocities are given. So by using this, okay, the Q of the model we can determine. So by using this, for solving data, Q of the model, all the data were given, we found out 1.19 feet cube per second. Okay, so by using this we can easily determine the pressure drop from the chart. So let's see for the equation of the pressure drop. So here you can see we have a Q of model is equals to 1.19 feet cube per second. So go back to the curve. So here you can see 1.19. So 1.19 is somewhere here. So you take a vertical line, you hit it somewhere here, and then take a horizontal line up to here. So you are getting 2.9 or 2.8 something more or less. So let's see what we have considered. So we have considered the QM is equals to 1.19 feet per second and delta PM is equals to 50 feet. Let's see once again from this chart. Okay, 03 1.19. Sorry, 1.19. Okay, so 1.19. So 1.19 is going to be somewhere here. Sorry. Okay, so 1.19 is somewhere here. 1.19 means 1.2. Sorry about that. So 1.2 is, this is the line for the 1.2. We go straight. Okay, and then hit the curve, and then finally we got the pressure drop across this flow rate. So the pressure drop we got across this flow rate is somewhere 5.5 something. Okay, so this exactly what mentioned here. Okay, so from the graph we got this value. So we we write down the same pi term for the model and as well for the model as well as for the prototype, this the first pi term, and we separate all those values and we make the delta P of the prototype as a function of delta P of model. So this is the ratio of angular velocity, this is the ratio of the diameter. So but if the density is same, if density is same, not same, if we are using some other model fluid, so we can take the ratio of the density as well. Okay, since the density of the water model and the density of the prototype fluid are same, so we cancel them each other, and finally this is the relationship, and we can calculate the values by putting all the given data. So finally the delta P we got is 27.8 psi. So this is the pressure drop across the prototype pump. Okay, so you can see here in the model pump is the pressure drop is very less, but in the actual one the pressure drop is much higher. Okay, so let's move on to the last problem of today. A wind blows past building. Okay, complex flow patterns can develop due to various factors such as flow separation and interaction between adjacent buildings. Okay, so flow separation terms we have already discussed in the what is a flow separation. Okay, when the streamlines, when they are flowing in a laminar way, in a proper stream flow, if the flow got turbulent, so the streamlines got separated, the distance between the two streamlines start increasing. Okay, so in that case there the flow separation starts between the streamlines. So assume that the local gauge pressure P at a particular location on a building is a function of the air density. Okay, so the gauge pressure, the pressure, air pressure, that means atmospheric pressure measuring at a point on the building, is a function of the density of the wind and the wind speed, some characteristics length L and the other pertinent length Li. Okay, so characteristic length means the length of the building, or other length, just width or some other dimension that is indicating with Li. Need to be characterized the geometry of the building or building complex. So first of all, what we have to do, so the atmospheric pressure P at a certain point on the building is depending on these variables. Okay, so determine a suitable set of dimensionless parameters that can be used to study pressure distribution. First of all, we have to determine the number of pi terms by using a dimensionless pi theorem. And now the case 2, now they are reflecting to a practical problem. An 8-story building that is 100 feet tall is to be modeled in a wind tunnel if a length scale of 1:300 is to be used. So how tall should be the model building be? So first of all, we have to find out the size of the model if the building height is 100 feet. Okay, so third, how will a measured pressure in the model be related to the corresponding prototype pressure? Assume the same air density in the model and prototype. So based on the assumed variables, does the model wind speed have to be equal to the prototype wind speed? Explain. So we have to find out three things. First, we have to determine the pi terms. Second, we have to find out the height of the model or size of the model. And C, we have to determine a relationship between the prototype pressure on the building, the pressure on the prototype and the pressure on the model. So first of all, the first step is to write down all the variables in the form of dependent variables. So the pressure drop, atmospheric pressure drop on the building is depending on the following variables. Okay, we write down, we wrote them in the form of the dimensions, and finally we have 5 variables and 3 fundamental or reference variables. So we need two pi terms to explain this phenomena. So after solving that, we got these 2 pi terms. Okay, so this is the pi term for the prototype or for the real object. So let's move on. So first problem we have solved, we have developed the pi terms, and second problem we have to determine the height of the model. So for the geometric similarity, so this is the geometric similarity. We took this pi 2 and write down the pi 2 in the form of model, and this is the prototype. So ratio is given 1:300. So Lm over L, Lim over L. Okay, so this is the model height, and this is the prototype height. Okay, and this is the characteristics length of the model, and this is the characteristics length of the prototype. So, and it follows that all pertinent length are scaled with the length scale of Lm over L. Thus, with Lm over L is equals to 1:300 is given. Okay, so the model height. Okay, so the model height is 100 feet. The height of the actual building is given 1:300. So the model height would be 0.33 feet. Okay, so the model height would be 300, and whatever is the other lengths, they will be reduced accordingly with 1:300 scale. Okay, so now we are going to third term. We are going to develop a relationship between the pressure drop of the pressure drop on the building as a function of pressure drop on the model. So with the geometric similarity okay, satisfied, it follows that. Okay, so here we separate this term because we have to find out the pressure drop of the pressure drop at a point on the prototype or the real. So that is P as a function of function of density of the model over density, velocity of the prototype over velocity of the model. Okay, so here, since the density of the air are same, so we cancel this term from here. So finally P is the pressure drop on the building as a function of pressure on the model with the with the product of velocity ratio with a square. Okay, so here this is the relationship between the prototype and the model pressure drop. So here with this set we can say that the set of the given variable, the model wind speed does not have to be equal to the prototype because it has a multiplication with the ratio of the pressure drop. Okay, so if the pressure drop varies, definitely the velocity on the model and velocity on the prototype would not be the same. Definitely it would be different. Okay, so here are the solution of all the problems we have did. So this is end of the dimension analysis chapter.